Okay, Objective 7.3 is looking at evaluating the actual thematic data in the field. So I'm going to talk about everything again from like the beginning right to the end and how you would actually collect that data. So the the first thing you need to do is plan, right? We talked about how important planning is with thematic data. So what you're going to do is establish what you're going to measure and to what detail, right? Again, remembering that our satellites only collect so many or like such a certain area and spatial resolution, right? So as you're working with that spatial resolution, what do you actually need in the actual pixel to figure out what is providing me that information? Now, something to keep in mind too is that there can be one item in a a pixel that maybe has a really strong reflection rate in a certain band, and that's going to dominate the entire pixel. You can also have like a dark pixel, and that pixel might be really dark because of one item. Like, and it may not be very large, but it can really it could be like the big absorber. So you do have to have enough of a detail to capture that, but not too much detail where you're collecting, every leaf size on the tree. So that it's a big balance, right? So you really, what can you pick up when you're out there? Then also know what classification scheme you're using. So if you are looking at land cover types and you're starting to get into like rooftop types, and you're like, oh, I need to know what kind of rooftop it is. So that is a different kind of classification than just saying that it's a residential area. So that is um, that's something to keep in mind as well. So only collect the data that you are looking at and that you want in your final product. Then we also need to worry about reference materials. So make sure you have everything that you might need. So like old observations. It's just like going out and surveying. If you have done a job before, you want the old file because then you want to see what everybody else has done before. So make sure that it's the same thing here. Going out in the field, take whatever observations that somebody has had before, because then it's really just updating it. Then bring any aerial photos. So if you're dealing with satellite images, bring any aerial photos that you have access to, because those have a higher resolution and you'll be able to see a little bit more detail, and it might make it easier for you to see that transition from terrestrial to air to satellite. And also bring maps. You cannot rely on GPS everywhere you go. When I was up in the Arctic, we couldn't use handheld GPSs because all of the GPS signals were within the 10-degree horizon. So our accuracy was like 300 meters, so I could totally miss the entire island that I was supposed to be working by. Then we have simple observations. So we don't want to be again, too detailed unless you need to be. If you're doing a hyperspectral remote sensing project, then you need to be a lot more complex. But for most observations, we're kind of keeping it simple. So is it grass or is it a shrub? That kind of thing. Now, that definition may be challenging for some of you because you're like, I don't know the difference between a deciduous and coniferous tree because of whatever reason, or I don't know the difference between a shrub and a baby tree. Like, how do I tell the difference? And because that's more like ecology than it is, and that's fair, that of course, right? So you would be working in an industry that you would learn about that. So your observations stay simple, especially when you're dealing with thematic stuff. And then you need to know what you're looking for and what you're looking at. So if I'm looking for coniferous and deciduous trees, then I need to look at and say, do I know what a deciduous tree looks like? And is that a deciduous tree? So, or one of the trickiest ones, and I'm going to use this as an example, is larch trees, because in the alpine regions, larch trees actually lose all their needles. They're a coniferous tree, but they lose all their needles in the winter. So they actually look dead. So it's like, oh, it's a dead tree. But no, actually, it's a live tree. It just grows back all its needles every year. So, so you have to know, oh, this is a larch tree. It is not a dead spruce tree. So again, that you would be trained in those areas if that's what you're going to be working with. Um, with your measurements itself, so for example, if we're looking at forestry, we might be looking at density of the forest, we might be looking at crown cover. If we're looking at like waterways and hydrography, we might be looking at water depths and the salinity of water. If we're dealing with agriculture, we might be looking as well as density of the crop and looking at soil moisture, et cetera, et cetera. So there's lots of stuff to look at. Then we go out and we look at our training sites. So we figure out on our image, where do we actually want to go? So if you do a supervised classification, you already have those. So go out to those training sites. Make sure that when you place them on your map, that they are areas that you can actually access, right? Then you get to identify the class composition based on land cover. So that is sometimes before you go out there. So what constitutes each of the land cover types and what am I looking for? What kind of information do I need? Then once you have done that, you can identify your features in the image. So you're like, okay, these are trees, this is crop, this is water. Then you need to develop data for spectral biophysical models. So this is like looking at like an NDVI. So what do I need to know for that? The reason why I need to know that, and this would be something you're trained in your industry that you're working in, is because I need to know what data I'm collecting. So if I'm collecting salinity, then I need to know how to collect that, and I need to know why I'm collecting that, because otherwise it's just, yeah, I could end up making a mistake and not doing it correctly. Then there's 3 criteria of acceptability for measurements. So measuring must be defensible. Okay, so that means that every time that you go out, you need to be able to prove that you have done it in a way that's systematic and that you can measure errors and that you can go back and prove it again. Another one is that the data must be representative of the population being measured. So don't go and you're like, oh, I hate coring trees. I'm going to go to this little tiny baby tree and I'm going to core it instead, even though there's only one of them in the entire area. Then that's not measuring, being representative of the population. And then also the data must be in a form that is meaningful to the user of the final product. So that means any field work that you have done, you need to have it written out in a way that they understand it, which is a great lead-in to field notes. So there's going to be 3 pages of field notes for every time you go out. You always have a title page. That doesn't change with remote sensing. You're going to have a title page that has the project, date and times. Time is actually really important for remote sensing because if you're trying to do anything in situ, then you need to know when you were out there. Crews and the crew that's out there, the roles that they took, any equipment that you took out there, what the weather looked like, any photo identification. So you could take a photo of the area and say put that on the title page. You don't necessarily need that one. That one's kind of, it can kind of go in between 2, but sometimes it helps. You can have you need to have the coordinates of the center of the grid so that you can relocate it again. Any slopes or angles and aspects of the land, and any land use. So what's going on? Is there construction going on? Is it residential? Is it agricultural? Is it natural? Is it a forest? Is it meadow? All of that. On page 2, you're going to actually have a table of information. There are some examples in the field methods for remote sensing textbook that all of this, like everything that I'm talking about here, is also found in, and I've referenced it for you in the module online. So there's a bunch of different pages there that you can check out, and there's one specific to Thematic. But so your page 2 is going to have all the information about what you were observing. I want you to imagine when you go out into the field that you are a column. So when you are measuring, you're going to stand in the spot that you are sampling, and you're going to pretend that there's a column around you. You cannot see past that point. So what is below you? What kind of soil is below you? What kind of grass is below you? Is there a bush there that you're standing in? And then you're going to move your way up the column all the way up into the sky. So obviously the sky doesn't need to be like, oh, it's cloudy today, because obviously you won't see anything with a passive sensor. But you would go up to like the top of the trees in that column. If there are no branches above you, even though there's a tree beside you, you don't include it because your column does not include that tree. So think about it as like as wide as your feet or maybe as wide as your shoulders, and what you see in your column is all you're going to see. Okay, so that's what you're writing down. You're not going to write about something that is 2 meters away because that is another sampling point. So only what you have in your location. Then we have page 3, which is your field sketch. I would expect that you do your field sketch in a way that it looks like a topographic survey. So you're going to have all your land features, you're going to draw your grid, which you've laid out. You're going to show all the points with the ID numbers. You're going to show topographic information, you're going to have a north arrow, you're going to have legends, and any names who did up the report of it. So page 2 is all of your sample points. So you can either have a great big table with all of the sampling information, or you can go to those pages that are in the textbook, and you're going to write those for each individual point that you do. So this can become a very big report, right, of your sampling, and that is okay because the more data you have, the more likely you're going to be more accurate. And if you're getting paid to do this, then they may tell you you have a certain time frame, so then you're working around that time frame. So you'll find efficiencies in what you need to do. So the next objective is looking at a vegetation evaluation method. And so vegetation itself, I'm going to give a little bit of background about vegetation. The reason I bring this in as an example, as basically an application, is because if you work in agriculture, and agriculture is like a really big industry in Alberta, more so it's actually bigger than oil and gas. So, and then if you go into BC, you're looking at a lot of forestry applications, and there's also agriculture there as well. So vegetation is really a big deal. Environmental applications, we always look at vegetation. So looking at leaf, we have to look at leaf pigment. We have to understand what leaf pigment does and what it is. So we've already talked about chlorophyll. So the chlorophyll, it doesn't make leaves reflect green and near infrared, but the chlorophyll, it's the mesophyll that does that. But the chlorophyll is used to do photosynthesis, so it absorbs the red. And so a lot, like the common knowledge is that, oh, chlorophyll does all this work. So that's why this is here, because if you read the textbook, that's what they state. And but it's the mesophyll that actually reflects the near infrared and not the green. So the near infrared is reflected by mesophyll. Chlorophyll absorbs red, reflects green. Really important that. Then we have what happens when there's dehydration. So dehydration, or like harvesting crops like the senescent crops where it goes all brown, that reduces the amount of chlorophyll. Then red and blue bands increase for reflection, but the green actually reduces. Then we can there's also different parts of the plant. So there's carotene and xanthophyll, and that actually reflects yellow and brown. So as those increase, we're going to see that. That is often found in trunks as well of the trees. Then we have something called anthocyanin, and that also reflects red. So if that increases, then we end up with more reddy color leaves. So these are the colors that the trees and the leaves turn in the fall, and it's based on these particular properties within the leaf itself. If we lose all pigment, any of the pigment that's within the leaf, it actually increases the reflection in the visible light. So it's starting to like even out, right? Where it would almost look like a soil line at that point. So if we go into like dry areas versus humid areas, the vegetation is all different. So everywhere you go in this world, you're going to have a different kind of leaf pigment that you're dealing with. And it's all based on some of these terms in here. I don't expect you guys to be memorizing carotene and xanthophyll and anthocyanin. I'm more concerned about you knowing mesophyll and the chlorophyll. So then the leaf structure, the actual structure itself affects the near infrared, like I said. So mesophyll of the leaf is the composition of the plant and has a higher near infrared reflection when it's a strong structure. So we've talked about that before, and I just mentioned it on the previous page. Energy transmission. So half of the near infrared transmits through the leaf and the other half reflects. So it's a 50% transmission. This also impacts our biomass numbers and our leaf area index numbers. So we have to be aware that near infrared will transmit through a leaf. So that means that if you're standing under a leafy tree, near infrared is still making it through. Then we also need to worry about plant moisture content. So you would often collect leaves and put them in a bag, and then you can measure it later, like by dehydration, using weights, and there's other ways as well. Timing of the measurement and crop calendars are really important. As you can imagine, plants change rather quickly. In the Arctic, within 3 days, I can have like no vegetation to having like super beautiful flowers everywhere, and then it's dying off within 3 days. So vegetation can really change very fast and makes things a little bit more challenging. There are a lot of standards in forestry and agriculture, so if you do decide that you want to work in one of those industries in remote sensing, you're going to have to spend a lot of time learning that. So other methods of measuring vegetation, it's the same idea. You still have those same 3 pages. I'm just going to cover this a little bit faster now because now you know how to set up your field notes. So if you go out into the field, you can use something called a line intercept method, which is what I was talking about with my similar to my transects where I would like make an L shape. This one now I'm going to make a cross. So this would be similar to a not the stratified random, sorry, the systematic unaligned pattern. And then, or you can use quadrats. So you would create your 3 by 3 pixels, and then you would create more quadrants, and then you'd have like little areas that you're actually sampling the smaller vegetation in those areas. You can also do a lot of volume and weight analysis. So this is a little bit more destructive, where the other ones are a little less destructive, but you can collect all kinds of information using volume and weight analysis. So that was vegetation. Moving into soil, soils are really interesting because there's all kinds of stuff that happens in them. So in the visible wavelengths, reflection increases and absorption bands become less pronounced until they essentially disappear in sandy soils. So sandy soils have a huge amount of reflectance. Clay and loam tend to have a little bit less reflectance. So reflectance and absorption are kind of opposite of each other. It's like error and accuracy. Then we have clay and silt. As we increase clay and silt, the moisture absorption bands diminish, but remain visible during drying. Okay, so again, looking at a lot of soils, instead of looking merely at reflectance like we do in vegetation, we're looking a lot at what gets absorbed, because soil tends to have a very high reflection, especially in the infrareds, but in the visible light, it tends to be a little bit lower. So we're more worried about what is absorbing it. And then we increase moisture, decrease reflectance, and it quickly hits a plateau, right? So we have this really sharp upswing in the near infrared spectrum. As the wavelengths get longer, it goes higher and higher and higher, and then it plateaus off. So also, if you have too much moisture in it, then we end up actually it ends up becoming like a puddle. So near infrared actually reflects much less, and then it just becomes 0. Soil texture also has an impact on the visible wavelengths. So small particles hold moisture better, so they appear darker, which makes sense, right? Wet soil tends to look very black, and especially like loam if it's very moist. And then if you have larger particles, like getting into like a sandy, gravelly type of soil, that holds much less moisture and it does appear lighter. So reflectance tends to be higher as the particle size decreases and the surface becomes smoother. Okay. So the reason is as long as we remove moisture out of the equation, If we have a smooth surface, it is going to reflect back. It's going to have a higher reflectance. If it's really rough, it actually is diffuse scattering, so we reduce the amount of energy that's actually returning. So that's why soil texture is actually an important thing for us to note down. You'll actually see lines in crops if you're just looking strictly at a bare crop area. And depending on the sunlight, you might actually see lines in the ground. So you can be like, oh look, they just plowed that field. We can also look at organic matter. So as we increase organic matter, the reflectance decreases, so it becomes more and more absorbed. It maxes out at 5% organic matter though, so then it just kind of plateaus again at that point. Iron oxide also has an impact on visible wavelengths because it tends to go red as it kind of rusts out. So it's kind of an interesting thing if you've got that in your soil. Infrared. Well, clay absorbs radiation. Calcite absorbs radiation. Hydrocarbons also impact the infrared wavelengths, and there's many other minerals as well that are also in soils. So we know that soils have a huge impact on measurements because it's so high of reflectance in all of the infrareds, and it's a little bit lower in the visible, and then moisture really impacts it more so than you would see with vegetation. So there's a few things that we need to measure with soils. We need to measure the texture of it, how rough it is. We know what the organic matter is, so you might have to take it back to the office and measure that. You know the color, the structure of it. Is it dense or is it loose? Roughness, which I mentioned earlier. Moisture, of course, soil chemistry, and so on, because all of these different components of the soil impacts it. You also need to know the slope of the ground. That is also really important. So make sure that you know that, because depending on the angle of which this energy is reflecting back, it's actually really causes a lot of problems with soils. So if it's steep slopes, it causes a lot of problems with trying to measure soils. Then moving into snow and water. So this is water, not so much as my expertise, but snow for sure. Water, reflections come from within and on the surface. So there are some wavelengths that do penetrate into water. The wavelengths can transmit through the water to about 1 meter before they get absorbed. Some of them anyways. Not infrared. No, infrared will not. But if you can get that 1 meter, you can actually see the bottom, right? So in shallow areas, which is really handy for looking at trying to measure coastal regions or shorelines and those types of areas. As we increase turbidity, which is like particles suspended in the water, the depth of the energy penetration decreases, which makes sense, and the mapping of the bottom is reduced. If you are working in shallow water, sometimes it's really hard to determine the bottom or suspended matter in the water. So again, if it's being windy one day and you have like a bunch of materials that are like soils and sands and stuff that are floating in the water and suspended, it's probably not a good day to go out and do any measurements with the remote sensing, just because you don't know which one, if it's the bottom or if it's just suspended matter. So a few things that you want to measure or view or take a look. You can look for algae, floating oil, suspended particles. We cannot see gases, inorganic salts, or acidity when we're doing remote sensing. So those are the 3 things that you cannot measure. That would be more in the environmental monitoring group where everything goes back to the labs. That is a little bit different than what we are. We're looking at stuff on surfaces and like suspended that you can actually see with your own eyes, really in water. Because if you can't see it in the visible light spectrum, then the water's already absorbed it. So if you can't see a gas, then you're not going to see it in the satellite image. So field measurements that you would be looking at is suspended sediments. So you'd actually like take water samples, the turbidity, again, water samples, transparency, which you can measure in different ways, and any depth measurements. So if you're looking for the bottom, how deep is it? So moving into snow, this is what I worked with. Visible and infrared are pretty much 100% reflected. So snow is it has a huge albedo, very, very high albedo, so very high reflectance. Wet snow has a lower reflectance than dry snow, and that's really an important aspect to remember as well, because now we have suspended water within my snow. So that's a thing to measure. So that also tells us temperature. So that gives us an idea of how warm the snow is. Other things to sample if we're out in the field is crystal size, how well the snow is packed together, so cohesion, and how wet it is. So those are the three things that you would sample for optical remote sensing. Microwave remote sensing, we also do temperature, we also do salinity if you're on sea ice, and we do dielectric, so conductivity. We measure that as well. And yeah, density, so we'll actually like take samples from each layer of the snow and then take it back to the lab and measure the weight of it. So there's 5 classifications of snow. So there's 5 ways to do it anyways. So that's based on depth, it's based on density, it's based on hardness, and it's based on temperature. So those are the 4 factors that go into the 5 classifications. So that those are, if you're trying to classify snow, then those are the 4 things you're definitely going to be measuring. So then last but not least, we're looking at the urban areas, which I think some of you guys are going to be doing your labs within urban areas. So what we're concerned about here is that we're looking at earth or rock, vegetation, and water. There's a lot of stuff that's involved in urban areas. At this time of year, you may be looking at snow as well. And that's okay. As long as you know your area well enough, then you can be like, I actually know that there's pavement underneath here. I know that this is a, lawn. I know that this is a field. You should be able to tell it's a tree. The tree, we shouldn't have snow that high. So that's okay. High spatial frequencies is the issue in urban areas. So we do need to remember that, because it's just like there's so much detail and location is an issue, and there's a lot of stuff going on there. Vegetation does tend to decrease as we go from low densities to high densities. Actually, I have a family friend that family friend, I guess you would say that. So they're from the Czech Republic, and she's a city architect and in Prague, and they are actually studying North American downtowns, because they are having major flooding issues in Prague. They've never had issues before, ever since like Prague has been around, but they're having serious flooding issues, and it's because they don't have any vegetation in their downtown core. It is all like concrete and cobblestone and buildings. So as the climate has changed, there's more moisture coming into Prague, and it's all pooling and causing flooding. So they're trying to find ways to mitigate this through adding vegetation to their downtown, like using trees and other kinds of plants, so that they can actually absorb it. So so that it's definitely a case out there, because if you go to the countryside, it is all vegetation, obviously, and then as you move into the city, you start losing more and more vegetation until you're in the center. So construction materials also have a lot of the same properties as bare ground. So you think about your rooftops, it's probably asphalt rooftops. You might have metal rooftops. You might have rubber rooftops. You might have pavement on the ground. You might have concrete, or you might have cement somewhere. you might have rocks that are put in. Like there's all kinds of stuff that like all these construction materials all look like bare ground. As long as there's no water, they reflect very, very strongly. So that we have to find out what is that dominant reflectance coming from. It is handy to have aerial photos as well. So there's some examples of this is like where you would use urban land or urban area remote sensing for is land use, socioeconomic studies, hydrology as well. And like I was mentioning, the architect that's looking into it and trying to figure out vegetation, that would be another example. So lots of different examples there. Of course, remote sensing has so many applications. That is why we do field work, and that's why we go out and check on it to make sure that it's actually correct. So that wraps up our fieldwork theory, and we'll be moving into thermal in our next module.